the last few lectures, we have been endeavoring to find optimality conditions for constraint optimization problems. We notice that we have found two such conditions, but those two conditions are geometric in nature and thus they are called as geometric optimality conditions. But we see that verification of geometric optimality conditions is not really an easy task. So we always aim for finding algebraic optimality condition. In this lecture, we are going to talk about one of the mostly used optimality condition, that is the Karus-Kuhn-Tucker optimality condition for constraint optimization problems.
I welcome you in this most important lecture of the entire course, the KKT necessary optimality conditions. If we recall our last day's lecture, we will find that we were discussing about the notion of tangent cone. Then we were trying to interrelate the cone of feasible directions, the tangent cone and the linearizing cone. We have found that the cone of feasible direction is a subset of the tangent cone and tangent cone is a subset of the linearizing cone. We have also seen two other examples where we have seen where the tangent cone might be equal to the linearizing cone and tangent cone might be also strictly subset of the linearizing cone, and a sequential representation of the tangent cone was also given. And then I was thinking to give on the last day's lecture the geometric optimality condition. Time was not there, so we shall continue today's lecture in the geometric optimality condition 2, in which we will observe that it is in fact a necessary optimality condition, where we will observe that if a point x0 is a local minimizer of a constraint optimization problem, then the cone of the descent directions and the tangent cone at the point minimizer at the point x0 must be equal to empty, and from this geometric optimality condition we will find the KKT necessary optimality condition. So let's start our class with the geometric optimality condition 2, which neatly states the following. It is geometric optimality condition 2. It says that if x0 is a local minimizer of the constraint problem that we have written here, the problem P. We will always refer by constraint optimization problem this particular problem, minimization of the objective function f subject to gix less than equal to 0, hx equal to 0, and here the set capital X is non-empty. Pre-assume that X is also open and non-empty. Why do we take here the openness of the set capital X? Because you all know that the necessary optimality condition, the Fermat's law for unconstrained optimization problem, it is valid if the minimizer is an interior point, and therefore we consider capital X to be open so that any element in the set capital X is an interior point. And here also we do assume that unless otherwise stated, we will assume all the functions f, gi, aj all are continuously differentiable. Only once differentiable we are assuming. If we require later for second order necessary and sufficient optimality condition, we will mention therein that the objective function and the constraints are twice continuously differentiable. In some problems, we will assume that the functions are not at all differentiable. Those are non-smooth type of problems. However, in this course, we will not talk about non-smooth optimization problem and their optimality condition. So unless otherwise stated, let me be neatly mentioning here that unless otherwise stated by constraint optimization problem, we will mean this problem where the set capital X is open and non-empty subset of the n-dimensional Euclidean space, and also the objective function f, gi, aj all are continuously differentiable. Well, so here in the geometric necessary optimality condition 2, if x0 is a local minimizer of the constraint optimization problem P, then we will observe that the gradient of f at x naught must be lying in the dual cone of the tangent cone, and from here it is trivial to observe, and hence you will have the intersection of the tangent cone and the cone of descent directions at the point x naught is an empty set. Well, let me just quickly prove this result, and then we will get into the KKT optimality condition, which will be just derived with the help of this geometric optimality condition too. Now here we note the following, that in the lines of the proof we have the following. We note that x naught is given to be a local minimizer, and what do we have to prove? We have to prove that grad f x naught is belonging to the dual cone of the tangent cone. So let me consider an element of the tangent cone at first, and then if I just take an element y in the tangent cone, and if I can show that from here grad f transpose y is greater than equals to 0, then obviously this vector grad f x naught must be belonging to the dual cone of the tangent cone. That is the definition of the dual cone, right? So here let us start our proof with letting an element y belonging to the tangent cone at the point x naught. And by the definition of the tangent cone, as y is an element of the tangent cone, therefore there exists a sequence xk in the feasible set with xk converging to the element x naught, such that we will have xk minus x naught divided by norm of xk minus x naught, these converging to y divided by norm y. Fine. So here without loss of generality you just go with the proof for y not equals to 0. So here you can just state here, if y is equal to 0, then obviously grad f x naught transpose times 0 is greater than equals to 0. So here without loss of generality you can just assume that y not equals to 0, or let me neatly write it. If y equals to 0, if y is null, then evidently you have grad f x naught transpose 0 is greater than equals to 0, and hence this is belonging to the dual cone, right? And let then y is non-null, then there exists a sequence xk such that the convergence that I have written at the bottom line. Now we notice that the element x naught is assumed to be a local minimizer, and the sequence xk is converging to x naught. So here let's suppose I have the point x naught over here, and as x naught is a local minimizer, therefore there exists a neighborhood of the point x naught. Let's suppose a delta neighborhood, and this is the radius delta, in which you will observe that f x naught is less than equals to fx for all x inside this neighborhood, right? That is the definition of local minimizer. And as x naught is a sequence that converges to the point x naught, then we note that obviously the sequential elements x1 x2 and so on, and after certain value of k you will have the xk belonging to this neighborhood, right? And therefore as xk converges to the point x naught, and x naught is a local minimizer, there exists, and these xk elements all are in the feasible set f, and therefore what will happen, this x naught, as x naught is an element of the feasible set, and x naught is, even if it is not an interior point, then you will note that you have here, let's suppose my feasible set is this much is my feasible set, let's suppose. And then we note that what will happen, that fx naught is less than equals to fx for all x not only in the neighborhood but also in the feasible set of the problem. This is due to the fact that x naught is a local minimizer of the constraint optimization problem, and therefore x naught is belonging to the set capital F, and therefore this is followed due to the fact that the point x naught is a local minimizer of the constraint problem. Now here you note that as xk is belonging to F and x naught is a local minimizer, therefore what will happen is that 0 less than equals to fxk minus fx naught, and this will happen for all k greater than equals to some natural number. Let's suppose it is p. For some p belonging to the natural number set, and this xk element is inside the set F for all k, and therefore what will happen, that xk element which is belonging to the neighborhood, obviously that will become inside the set capital F, and hence here from here we note that this fxk minus fx naught, now we consider here a Taylor series first order approximation, then you will have this equals to gradient of fx naught transpose into xk minus x naught plus small o of norm xk minus x naught, right? Now from here we note that this implies, so on both the sides we divide by norm of xk minus x naught, and then you will have gradient of f x naught transpose xk minus x naught divided by norm of xk minus x naught plus small o of norm xk minus x naught divided by norm of xk minus x naught, and this is greater than equals to 0 for all k greater than equals to p. Now as k tends to infinity, on the left hand side what do you have is that gradient fx transpose into y divided by norm y plus this element by the definition of small o is equal to 0. This is greater than equals to 0, and hence you have that grad of f x naught transpose y is greater than equals to, and this is true for every y because no restriction on y was taken. You have taken any element y inside the tangent cone. If it is null, then you have seen that this grad fx naught is belonging to the dual cone. However, if y is not null, then in this case we have seen here that grad fx naught transpose y is greater than equals to 0, and therefore arbitrariness of y gives that grad f x naught is belonging to the dual of the tangent cone, because you have grad f x transpose y greater than equals to 0 for all y in the tangent cone, and therefore you have grad f x naught belonging to the dual cone. Once you have this, then immediately what we notice that, now what we notice from one, that for every y in the tangent cone you have gradient of fx naught transpose y is greater than equals to 0, and therefore what is happening is that y is not belonging to, one implies y is not belonging to the cone of descent direction, because if y is in the cone of descent direction, then grad f x naught transpose y must be less than 0. So any y that is in the tangent cone cannot belonging to the descent cone of the objective function, and therefore what you have is the cone of descent direction and the tangent cone has empty intersection. Fine. That is what the proof. Very simple it is, and it is followed from the definition of the tangent cone. And the geometric optimality condition is both of the things are equivalent, either this or this. Eventually, in several textbooks, they do say that this is the optimality condition. However, the first one is also an optimality condition because from here itself, this one has been derived. Now, let me see geometrically what does this geometric optimality condition says. It says that if x0 is a local minimizer, then grad f must be belonging to the dual of the tangent cone. Now, let me hypothetically draw out a feasible region, and there let me locate the dual of the tangent cone. Let me take this is my, let me say my feasible set is this. This is my g1x less than equals to 0, this side, and here is g2x, boundary is g2x equal to 0, and the feasible region gives this side, and here it goes g3, and let me say this is my point x0, and the contours of the objective function are, let me say the contours are as follows. This is level c1, this is level c2, this is level c3, and that goes your, at this point you have a local minimizer because here you know that here is c1, at this surface you have c1 value, at this surface you have c2 value, at bigger surface you have c3 value, and c1 is less than c2 is less than c3. And obviously if you go a little bigger, then obviously that value is not a minimum value because you will have a bigger value than c4. Let me consider, if I consider this much is the contour from where you have c4 value of the objective function, and c4 will be greater than c3, and therefore this c4 cannot be a local minimizer. However, c3 is the smallest value in the feasible region. Although c1, c2 are much smaller than c3, but they are not feasible value. And therefore, what you have is that this point in this figure, you know that this is your feasible region, this is your feasible region, and this point x0 is the minimum element. Now let me try to locate the dual of the tangent cone. The dual of the tangent cone is given by the following figure. Here you note that what is the tangent cone? Here obviously the tangent cone is this one, that at this level you draw the tangent, and at this level you draw the tangent, and therefore tangent cone is this one. Tangent cone is this green dotted region. Some of the points in the tangent cone, they are not visible. Okay, they are coming out to visible. However, sequentially, if we move to the extreme directions, the green directions, then you will be able to lead to only visible region. That is the definition of the tangent cone. Now, here we note that what are the binding set, the index of the binding set. Let me consider to identify at the point x0. At the point x0, your binding set or active set are those indices i's for which gi x is equal to 0, and therefore ax0 contains only two indices 1 and 2 at the point x0, right? Now here goes your the green shaded region is your tangent cone. Now what is your dual cone? Dual of this tangent cone, the dual of this tangent cone gives the following figure. How do we find the dual cone of it? Dual cone obviously will be given by you find the extreme directions of the tangent cone, then you take the perpendicular to the extreme directions that we have learned during the discussion of the dual cone. Now let me draw perpendicular to the lower boundary of the tangent cone, and you will get a perpendicular as this one. This one is perpendicular to the lower boundary of the tangent cone, and for this line you have a perpendicular line as this one. Fine. And hence your dual cone is coming out to be this blue shaded region. This blue shaded region that I am dotting right now, this is your dual cone. Fine. Now at the optimum point x0, what is your cone of descent directions? Here you note that the gradient direction is obviously at this point, gradient direction is outward normal to the surface of fx is equal to c3, right? And outward direction that gives us this one, and it is perpendicular to the tangent at the point x0, to the tangent at the point x0 to the surface of fx is equal to c3. So this region is your cone of descent directions, because only in this region you have any direction d that makes more than 90 degree with the gradient of f at the point x0. Fine. This goes your c of descent direction x0, this orange shaded region, and this orange arrow is your grad f x0. Now here trivially from this figure you observe that at the optimum point you have that the intersection of the cone of descent directions and the dual of the tangent cone, this blue region, this is your dual of the tangent cone. They have empty intersection. Fine. Once they have empty intersection, then we note that from this figure we are observing that they have empty intersection obviously, and not only in this figure, in every figure that you can draw. This is one just hypothetical figure. Any figure you can try to draw on your own, and you will find that at the optimum point x0, the tangent cone and the cone of descent direction have empty intersection. And now here we note that your grad f is belonging to grad f x0 is belonging to the dual of the tangent cone. Now if this is so, then let me try to observe the extreme directions of the dual cone. What are the extreme directions of the dual of the tangent cone? Are this one. This is one extreme direction, and this one is another extreme direction, right? And here you note that what is this direction? This blue direction is nothing but it is perpendicular to the tangent at g1x. Fine. And obviously then this extreme, which is perpendicular to this green line, is grad of g1 at x0. Fine. Similarly, this blue line, this another extreme direction of the dual cone is minus grad of g2 x0. Fine. And therefore this dual cone is the set of all positive linear combination. That means you have lambda I multiplied grad of gi x0, and you take the summation of over all i's in the active set, lambda I greater than equals to 0 for all I belonging to the active set, I belonging to the active set. It's not that. Let me repeat once again. Here you note that the extreme directions, if my extreme directions are these for a cone, let's suppose this is one direction and this is another direction. Here goes negative of g I x naught. Here goes, let's suppose 1, and here goes g2 x naught, negative of the gradient. Then you note that any direction that you can think of inside this cone is nothing but a positive linear combination of these two extreme vectors, minus of grad g1 x naught and minus of grad g2 x naught. Fine, because here you note that the direction that I drew in between minus grad of g1 and minus grad of g2 can be thought of as, you note that here I can consider a parallelogram whose parallelogram whose and here you note that this much is, let's suppose, lambda 1 times minus of grad g1, and here this much is your lambda 2 times minus grad of g2. So we can think of the direction that I have taken here. This direction is diagonal of this parallelogram, where the sides of the parallelogram are lambda 1. Here obviously this lambda 1 is greater than equals to 0. Similarly, lambda 2 is greater than equals to 0. And lambda 1 times minus of grad g1 and lambda 2 times minus of grad g2. You add them up, you get this diagonal direction. And not only this, you take any other direction. Accordingly, you can draw a parallelogram whose diagonal is this direction. And accordingly, obviously, you will find that the CT x naught star, the dual of the tangent cone, is nothing but the positive linear combination. By that I mean the coefficient here lambda I is a positive linear combination of the negative of the gradient g I x naught, where I is an active index. Fine. And this condition, then what does it say? This condition says that your grad f x naught must be equal to I belonging to a x naught lambda I minus grad of gi. That is what it says. The optimality condition says that at an optimum point you will have this. Loosely this. You should have a theoretical justification for this. And obviously you have to take a restriction. Otherwise this condition might not be observed. So here from the figure, loosely we observe that the dual of the tangent cone is this region, but not always. Under certain restriction, that the dual of the tangent cone is obviously positive linear combination of the negative of the gradient of GIs, where I's are active indices. And accordingly, from this optimality condition, that grad f x naught is belonging to dual of the tangent cone. This gives us that grad f x naught at the optimum point x naught must be equal to summation of lambda I minus grad g I x naught, such that you have grad f is a positive linear combination of the minus of grad gi. Loosely, this is your KKT optimality condition. Let me in the next prove the KKT necessary optimality condition for a constrained optimization problem. It says the following. This is the principal result in this lecture note. In the entire course even, the principal result is the following. This is your first order KKT Karush Kuntakar. Karush Kuntakar, or abbreviated as KKT. First order KKT necessary optimality condition. Optimality condition for constrained optimization problems. It says the following, that you consider the problem that I was discussing at the beginning of this lecture. And you consider this problem where f, gi, aj are continuously differentiable and the set capital X is open and non-empty. And then, so here let me start with, let capital X be a non-empty open subset of the n-dimensional Euclidean space of Rn. Consider the problem P, and suppose x naught be a local minimizer of the problem, and the condition that we refer as constrained qualification or a regularity condition, and the condition that the linearizing cone, its dual, and the dual of the tangent cone at x naught, they are identical. Then there exists vectors lambda belonging to the first quadrant of the m-dimensional Euclidean space and mu belonging to the l-dimensional Euclidean space, such that you have grad f x naught plus summation I is equal to 1 to m lambda I grad gi x naught plus j equals to 1 to l mu j grad aj x naught is equal to null vector, and you have lambda I times gi x naught is equal to 0 for all I equals to 1 to m. Fine. Let me quickly prove this result, then I will come back to several discussion on this theorem. The proof goes the following way. Now, as x naught is a local minimizer, from the geometric optimality condition 2, what you have is grad f x naught belonging to the dual of the tangent cone, and dual of the tangent cone is assumed to be the dual of the linearizing cone, is not it? And once you have this, then you note that this implies and implemented by, note that for a feasible point, note the following: if your grad f x naught, if it belongs to the dual of the linearizing cone, then it implies and implemented by the definition of the dual of the linearizing cone, that grad f x naught transpose d is greater than equals to 0 for all d belonging to the linearizing cone, right? X naught. And once you have this, then obviously any d that is in the linearizing cone, as that satisfies grad f x naught transpose d is greater than equals to 0, obviously it cannot be less than 0, and obviously that gives you that the linearizing cone and the cone of descent direction x naught is equal to the null set, because the cone of descent direction has the definition that the d must be grad f x naught transpose d is less than 0, and therefore it is equal to null. Once it is equal to null, then what happens? You please note that if I consider the following system, the system that here you take d an element of the n-dimensional Euclidean space, the system, I consider here the defining set for the linearizing cone, grad gi x naught transpose d is less than equals to 0 for all I belonging to the active set, and you have the grad of aj x naught transpose d is equal to 0 for all j is equal to 1 to till L. That is the definition. The linearizing cone is the set of all D in Rn such that this inequality and this equality are satisfied. And for the cone of descent directions, the definition is gradient of f at x naught transpose D is less than 0. Fine. So if I consider this system for some D belonging to Rn, now, is this system feasible? This system is not feasible due to the fact that the linearizing cone and the cone of descent direction has empty intersection. So there does not exist any D such that which satisfies this and also this too, right? And the system does not have any solution. So let me write it in terms of the Farkas lemma so that the things will be very clear to you and you can apply the Farkas lemma very conveniently. So let me write here your minus of grad of the Farkas lemma's two systems are let me just quickly take you to the note of Farkas lemma. That note of Farkas lemma goes in theorems of alternative. Yes, here is the Farkas lemma. It says that if A be a matrix of order m by n and C is an n-dimensional vector, then exactly one of the following two systems has a solution. But the system one says Ax less than equals to 0 and C transpose X greater than 0. And you have, so let me just copy it here, and let me paste over here. This is your Farkas lemma. This is your Farkas lemma. This is your Farkas lemma. Now here let me write grad of f x naught transpose. This goes your C transpose X greater than 0, and for AD less than equals to 0 you have the following. For AD I consider we note that you have an inequality. Here are equalities. So this equality I break into two inequalities, and I do write these equalities by negative of gradient aj x naught transpose is less than equals to 0 and gradient of aj x naught transpose d is less than equals to 0, and these two are for all j is equal to 1 to till L. Fine. So this system does not have a solution. Now here equivalently you take here C is equal to minus grad of fx naught, and you take the matrix A having the columns grad of gi x naught transpose, then you take minus grad of hj x naught transpose is gradient of hj x naught transpose. So A is this matrix. Then system 1 of the Farkas lemma does not have a solution. What is the system 2? Let me just quickly write what is the system 2. In system 2 we will find the following, that you have C equals to A transpose Y for some Y greater than equals to 0. So there exists then Y. Here Y is not just m dimensional. You have these here, let's suppose P many in Ax naught, and here you have 2L many. So your capital M here now is equal to capital M in the system 2. This is your P plus 2L dimensional. And I break into two parts. For P I take mu, and mu belonging to are your set of elements in Ax naught, This is the denotation of the cardinality of the set X naught, the number of elements that you have in X. And lambda, well, I have written in the theorem lambda for inequalities. I must write here in the reverse way that lambda, and you have mu belonging to 2L. So let me take mu dash for these inequalities, mu dash belonging to RL and mu double dash belonging to RL, such that you have A transpose Y is equal to C. A transpose Y equals to C, that will give you, here Y is nothing but, here Y is nothing but this lambda mu dash mu double dash. So A transpose Y will give you that lambda transpose grad gi x naught, and obviously you will not have just one component, all the components. So let me write as lambda I into gi, lambda I into gi plus plus and here obviously we will have sum I belonging to ax naught plus summation of mu dash j grad of minus grad of aj x naught for all j equal to 1 to L, plus you have summation mu j double dash grad of aj x naught. Fine. And j is equal to 1 to L. This must be equal to C. C is your minus grad of fx. Fine. This is what happening by the Farkas lemma. By Farkas lemma, theorem of alternatives, there exists this such that this is fine. Now here by assigning, by taking lambda I is equal to 0 for I not belonging to the active index, and you also define mu j to be mu j double dash minus mu j dash. If I define, then we know that we have from this equation, let me say 1, we have grad f x naught. I bring the right hand side to on the left, and then I note that I belonging to ax naught with the sum lambda I grad gi x naught. Now here I can add for those i's which are not in ax naught, as I have assigned lambda I is equal to 0. So I can here smoothly take that I ranging from 1 to m lambda I grad of gi x. This is due to the fact that if I is not belonging to ax naught, then in that case the term lambda I times grad gi x naught is equal to 0. Plus you have j is equal to 1 to L mu j times grad of aj x is equal to 0. And not only that, we also have, we note that lambda I times gi x naught. If I is belonging to ax naught, then obviously your gi x naught is equal to 0. So this is equal to 0. If I not belongs to ax naught, then lambda I is equal to 0. And therefore lambda I times gi is equal to 0 for all I is equal to 1 to till m, and voila, your result is done. Right? That is what you wanted to prove. Now here let me speak a few words about the historical perspective of the development of the Karus-Kuhn-Tucker condition. Here Kuhn and Tucker, they are two persons from Princeton University. They have derived this result in 1951. Kuhn and Tucker, and they have entitled the article by nonlinear programming. Those are Harold William Kuhn and Albert William Tucker from Princeton University. They have developed this result and they approached to several journals, and Duke Mathematics Journal rejected the paper, and later on they were very frustrated and they published this article in the second symposium that happened in the Berkeley, second Berkeley Symposium on Mathematical Statistics and Probability. Why Karu's name is appended? Actually, what happens before the appearance of this Karu's-Kuhn-Tucker result, before the appearance of this necessary optimality condition, only the Lagrange's multiplier rule was known before us. The Lagrange's multiplier rule is applicable only for the constraint optimization problems where the constraints are given by equality restrictions that we all have learned in our calculus course. In IIT BHU, we teach this Lagrange's multiplier rule in the mathematics 1 course. You all have gone through. Or otherwise, if some of are not from engineering background, you must have gone at your BSc mathematics in the calculus course, application of calculus. You all have gone through with the Lagrange's multiplier. You recall that the Lagrange's multiplier rule is applicable for equality constraints. Later on, people were trying to develop optimality conditions for or methods for solving constraint optimization problems where the restrictions are not only given by equalities but also inequalities. From 1930 or so, people extensively were trying, and there were several works on identifying feasibility of a set of inequalities. And the thesis by T. Mochkin in 1939, which is a thesis on a feasibility of inequality system, linear inequality system. And it is very surprised that T. Mochkin's thesis only contains a reference of 36 papers. And in the bibliography, if you have 36 papers in a thesis, you can think how little is the development of even feasibility check for a set of linear inequality. Then all of a sudden in 1951, Kuhn and Tucker, they appeared with an optimality condition for a constraint optimization problem where the inequalities are given by not only linear but you can include non-linear. Fine. So any non-linear inequality you give, your Kuhn-Tucker condition, optimality condition is applicable. But after the appearance of the paper by Kuhn and Tucker, people have found that in 1939, William Carus, he is a product of University of Chicago, in his MSc thesis, which is entitled by minima of functions of several variables with inequalities as side constraints. And the same result that is derived by Kuhn and Tucker is even derived by Carus. But during that time, people were not keen to publish their research articles or their research findings. And therefore, Carus' work was although submitted to the University of Chicago, but it was not published. And therefore, you will see in several books this optimality condition that I have proved here by the name of KKT first order necessary optimality condition. They just entitle it as Kuhn-Tucker condition because Kuhn-Tucker are the person who have published their work first. However, as Carus derived much earlier than Kuhn and Tucker, to honor the name of Carus, the name of Carus is also appended with Kuhn and Tucker, and it is now popularly known as Carus-Kuhn-Tucker necessary optimality condition. Much surprising fact is that in 1948, Fridjohn has derived an optimality condition for constraint optimization problems where the constraints are inequalities, non-linear inequalities possible. That means the same problem that was taken up by Kuhn and Tucker and published in 1951. This work has been already published in the work by Fritz-John, and the Kuhn-Tucker optimality condition is just a corollary to the Fritz-John condition. And Fritz-John eventually is not a person from optimization. Fritz-John is a person from partial differential equation, and you will find that there is a very classic book by Fritz-John, which is a very popular book till today. Whosoever are doing research in partial differential equation, they must have gone through the book by Fritz-John. And Fritz-John has derived, possibly he has a single contribution in the optimization theory, and that contribution is flourished so much, and uh, possibly Fritz-John is the person who has given at the first place optimality condition for constrained optimization problem, who has eventually published. Although we can just think Karus did not publish, but it is not Kuhn and Tucker who has published the result. Although I am not saying that, I am not dishonoring Kuhn and Tucker. Their contribution later in optimization are really huge. Without Kuhn and Tucker, you cannot think of several optimality other type of conditions. But Kuhn and Tucker's condition is a corollary of the Fritz-John condition, and it is very pity that you will find that several textbooks they miss the optimality condition derived by Fritz-John. Fritz-John must be somehow tributed in optimization theory. He must have been honored in optimization theory because he is the person who has published at the first place the optimality condition. Anyway, whatsoever be the fact, we should follow the terminology that given by our forefathers, and they have given it as popularly Karus-Kuhn-Tucker, and therefore we will just refer it as Karus-Kuhn-Tucker optimality condition, and abbreviately KKT optimality condition, KKT necessary optimality condition. Fine. Now several definitions are in the place. These are the following that we'll define here now. A KKT point definition. A KKT point. A point x0 belonging to capital X is called a KKT point of the problem P if x0 fulfills the following four conditions. First one is the primal feasibility. That means the point x0 must be a feasible point of the given problem P, and the feasible region is denoted by capital F. And the second condition is the point x0 must satisfy the stationarity condition. Stationarity condition, that is, you have grad fx0 plus summation I is equal to 1 to m lambda I grad gi x0 plus summation j is equal to 1 to L mu j grad hj x0 equals to the null vector for some lambda I greater than equals to 0 for all I and mu j belonging to the real number. Mu j is unrestricted inside it, and dual feasibility, that the stationarity condition is satisfied for a lambda belonging to Rm plus. That means whose all the components are non-negative. Although it is already taken in the stationarity condition, let me remove in the stationarity condition that for some lambda I and mu j, that would be more appropriate to be considered in the stationarity condition, that for some lambda I and mu j you have this equality is true. This is called stationarity. This is due to the fact, as you all know, by stationary point we mean where the gradient value vanishes, and this is the same fact is coming out in the equation of stationarity. And therefore the stationarity condition is satisfied for a lambda belonging to Rm plus first octant of the m-dimensional Euclidean space. That means it says that the lambda i's are all non-negative. Lambda i's, where i's are the components of the vector lambda. Well, and the last condition is the complementarity condition. Complementarity or complementary slackness. Complementary slackness is the condition that with the lambda i's, those are satisfying the stationarity condition as well as the dual feasibility. So with lambda i's in 2 and 3, that means the lambda i's which are satisfying both 2 and 3, if we have lambda I times gi x naught is equal to 0 for all I is equal to 1 to till m, then we say that it is the complementary slackness condition. Why it is called complementary slackness? Because we know that in the constraint set you have gi x is less than equals to 0, right? Gi x less than equals to 0 or gi x naught is less than equals to 0. Now this is equivalent of, by adding a slack variable you can write it to equality like si is equal to 0, where si is greater than equals to 0, right? And therefore what happens, this lambda I gi x naught is equal to 0 is nothing but your si times lambda I is equal to 0, right? Si times lambda I, because si is negative of the gi x naught. If you have lambda I gi x naught is equal to 0, then obviously you have from here that si times lambda is equal to 0. As si's are slack variables, and therefore to get 0 you are multiplying lambda I. So lambda I is complementary to si to get their product to be equals to 0, and that's why it is called complementary slackness. Lambda i's are complementary to the slack variable si to obtain their product of the slack variable and the lambda I is equal to 0. That means if si is equal to 0, then lambda I may not be 0, may or may not be equals to 0. However, if si is non-zero, in that case lambda I must be equal to 0. That is what it says. Now, if a point x naught satisfies all these four conditions, then we call the point x naught a KKT point. And therefore, what does the optimality condition, KKT necessary optimality condition says? The KKT necessary optimality condition says that it is a very neat fact. Note that optimality, that means if the point x naught is optimum, then does it imply that it is a KKT point? Does it imply it is a KKT point? No, it is really not, because here we note that unless this condition is satisfied, that this regularity condition is satisfied, this regularity condition is very crucial in the necessary optimality condition. If this condition or some other constant qualification condition is not satisfied, may not be your optimum point x naught. X naught might be optimum, but it might not be a KKT point. It might not satisfy these two conditions. So we'll have one example for this. X naught is an optimum point. Even if your problem is a convex optimization problem, then also x naught might not satisfy this system of equalities. Fine. And therefore optimality itself does not imply that the point x naught is a KKT point, but optimality plus a regularity condition or a constraint qualification, that will imply that the point x naught is a KKT point. Fine. Now let me give an example of KKT point. Consider the following problem. Minimization of f(x1, x2), which is defined by x1 minus 3 square plus x2 minus 2 square, subject to, it is not such that, it is subject to gi x1 x2 defined by x1 square plus x2 square minus 5 less than equals to 0. g2 x1 x2 is defined by minus x1 less than equals to 0. g3 x1 x2 defined by minus x2 less than equals to 0, and h1 x1 x2 is the equality constraint x1 plus 2x2 minus 4 is equal to 0. Now let us check if the point x0, 2, 1 is a KKT point. Let us check. Now in order to check that it is a KKT point, what do we have to check? We have to check all the four conditions: primal feasibility, stationarity condition, then dual feasibility, and complementary slackness. Let us take up one by one. Here you note that x0 evidently is a feasible point. This is very evident. It is satisfying the primal feasibility because all the constraints are satisfied. So here you just write down the point x0 is a primal feasible point. Now you might ask this question. You might have asked while defining the KKT point that why do I refer not just feasibility but primal feasibility? Primal and here again a dual, we'll find that there is a close association with the Lagrange's multiplier function with the KKT optimality condition. If you define a function that is the Lagrangian function Lx lambda mu by the following, that fx plus lambda transpose gx, where gx is the vector value function, all the components are g1x, g2x, g3x and gmx, and here mu transpose hx. So here lambda transpose gx is nothing but, this term is nothing but summation of lambda I into gi x. Similar is for mu transpose hx. Now you note that once I define this function, and this function is referred as Lagrangian, and if I refer this function as the Lagrangian function, then the stationarity condition says that the gradient with respect to the variable x, L, x naught and lambda mu, where lambda mu's are the values they are satisfying this dual feasibility condition and the complementary slackness, then it is equals to 0, and that's why it is called, it is referred as the stationarity condition. The second condition is referred as stationarity. It says that x naught lambda mu is a stationary point of the Lagrangian function. With the help of this Lagrangian function, we'll find that we can define a dual problem for the given constraint optimization problem. We'll in fact see that for any minimization problem, there is a maximization problem which is playing role, which is hidden inside the problem, and that maximization problem is referred as the dual problem. Dual word is the usual antonym of the primal, and therefore the original problem is referred as the primal problem, and the derived problem, which is the maximization problem, is called the dual problem. We will have separate 3 to 4 lectures on the duality theory, and there it will be very clear how lambda and mu can be observed as the variable of the dual problem, as the variable of a maximization problem which plays a role hidden inside solving of the given constraint problem. Fine. And therefore here we emphasize that the point x0 is a primal feasible point. Then the second condition is about the stationarity. Now for stationarity we identify at first the index set, the active set. We see that what is the active set index? Ax0 is set of all is for which gi x0 is equal to 0. And you note that g1 at x0 obviously is equal to 0. And g2, g3 they are not. Fine. And therefore ax0 contains only 1, the first index, and we compute the gradient value of the objective function, gradient value of the constraint functions that which are active, grad gi g1 x0, and also we compute grad of hj because we will need all of this in checking the stationarity. That grad f x0 is, you just make a check that this is minus 2 2, grad g1 is the column vector 4 2, and grad h jx0 is the column vector 1 2. Now for the checking of stationarity, we consider the following equation to check if x0 satisfies stationarity. We consider the following equation, that grad f x0 plus is equal to 0, or here the variables are lambda 1 and mu 1, and what we are endeavoring, what we are searching for is lambda 1 and mu 1, some specific value of lambda 1 and mu 1 such that this is satisfied, and as well the dual feasibility, that means lambda i's are greater than equal to 0, that has to be satisfied. Along with the dual feasibility, lambda I value must also satisfy this complementary slackness, that lambda I into gi x0 is equal to 0. Fine. So let us search at first lambda 1 and mu 1 such that this equation is true. So here the variables are, here we note that lambda 1 and mu 1 are variable, and we are trying to find lambda 1 mu 1 which are satisfying this. Then later on we will check whether the lambda I values which are satisfying this equation, they are also satisfying the dual feasibility and complementary slackness or not. Fine. Now here then let us just plug the values of the gradients, minus 2 2 plus lambda 1 4 2 plus mu 1 1 is equal to 0 0. Or you have here, you check that lambda equal to only 1/3 and mu 1 is equal to 2/3, they are satisfying this. Fine. And therefore obviously your the point x0 satisfies the stationarity condition, therefore x0 satisfies the stationarity condition. Fine. And here you note that we have gotten only one value of lambda 1 and one value of mu 1. There can be some problem where for several values of lambda 1 and mu 1 this equation is valid. Fine. And what the KKT point is asking you to check is that you try to find at least one lambda 1 that is greater than equals to 0, and that lambda 1 satisfies the stationarity condition, the dual feasibility, as well as the complementary slackness. And with this lambda 1, then let us proceed and check whether this is satisfying the complementary slackness, because this is trivially feasible, dual feasible. as lambda 1 greater than equals to 0 by taking lambda 2 is equal to 0 equal to lambda 3. We notice that lambda i's are all greater than equals to 0 for all I 1 2 3. Why am I taking lambda 2 is equal to 0 equal to lambda 3? Because that is eventually in a proof itself of this KKT optimality condition, that the i's which are not in the active set, you define lambda equal to 0, they will automatically satisfy your lambda I times gi is equal to 0. Fine. And once you define lambda 2 and lambda 3 is equal to 0, obviously the complementary slackness condition is also satisfied. Here, therefore, x naught satisfies not eventually x naught, your lambda, therefore these lambdas satisfies the dual feasibility. And we note that these lambdas are corresponding to the point x naught. So x naught is solely responsible to get lambda 1 is equal to 1/3. If you would have taken any other point instead of 1 2, you could have gotten different values of lambda 1. Fine. And therefore in the definition of KKT optimality condition, although the dual feasibility check is not for x naught but hidden into the lambda I values that satisfies your stationarity condition, these lambda I values, mu j values, they are eventually dependent on the point x naught. If you change this point x naught from here, then obviously your lambda I mu j, they will be changing. And therefore the dual feasibility condition, although is a condition on the Lagrange's multiplier on the lambda values, but here these lambda values are obtained with the help of the given point x naught, and therefore lambda is dependent on the point x naught, and therefore the dual feasibility condition is also thought of a condition for the given point x naught. So here these lambdas satisfying the dual feasibility. Now let us check for the fourth condition, which is very trivial. Notice that lambda I times gi x naught is equal to 0 for all I 1 2. You please check this. Don't just blindly say that notice that this is happening, and then we declare then that the point x naught is a KKT point. Fine. Now let me give one example which is often a source of error, but before that let me prove the KKT sufficient optimality condition. This condition is indeed necessary, not sufficient. A point can be a KKT point, but it may not be an optimum point. Can you find one example for this? This is although very easy. Let me keep as a home task to you. Find a problem or construct an optimization problem, constraint optimization problem, for which point x naught is KKT point, but x naught is not optimum. Can you find it? Further hint let me give you. I have given such example at the starting of optimality condition of constraint optimization. When I have started the discussion on the constraint optimization, there I started with the Lagrange's multiplier. There I gave a problem in which you will find that the stationarity condition is satisfied, but the point is not an optimum point. And that's why I'm keeping it as a home task, or you can find on your own one. You can eventually construct a problem. Very easy it is, not difficult. But why this is happening, let me give you an idea so that you can feel that KKT condition is indeed necessary, not sufficient. Is the following. You note that for unconstant optimization problem, grad f x naught is equal to 0 does not imply always, that does not necessarily imply that x naught is optimum. Similarly is here that your for constant optimization problem, grad L, the Lagrangian function, grad L with respect to x at the point x0 with some Lagrange's multiplier lambda bar mu bar is equal to 0, and this might not imply that x0 is an optimum. Fine. The similar fact for unconstrained, you have seen that grad f x0 equals to 0 is not implying x0 optimum. Similarly, grad L is equal to 0 does not necessarily imply that the point x0 is an optimum point. Now, let me give you the first order KKT sufficient optimality condition theorem, that under which condition a KKT point is an optimum point. Here the condition is very simple. If your problem is a convex optimization problem, then in that case the first order necessary optimality condition will become first order sufficient optimality condition. Like in unconstant optimization problem, you have seen that if your objective function f is convex, then grad f x0 is equal to 0 implies the point x0 is not only local but also a global optimum point, global minimum point that we have seen. Similar is the fact if your problem is a convex optimization problem. But what do we mean by a convex optimization problem? By a constraint convex optimization problem, we mean a problem of this type, a minimization problem of a convex objective function subject to x belonging to a convex constraint set. Your constraint set must be convex. Now, if I try to just write it in the following manner, if I attempt to write equivalently by the following manner, that it is minimization of fx subject to, can I take here that gi x less than equals to 0, h j x is equal to 0, where f gi h j are all convex. If I have f convex gi for all I equal to 1 to till m, h j x for all j belonging to 1 to till l. If I take f g I h j all are convex, is this problem a convex optimization problem? The answer is negative. This is due to the fact that although the set of all points x's for which gix less than equals to 0 is a convex set, no doubt on that, because gix convex implies that the sublevel sets are all convex. It's not that. However, if Hj is convex, it is not necessary that the set of all points x's such that Hjx is equal to 0 is a convex set. For instance, you take this function Hx1 x2 is equal to x1 square plus x2 square minus 1. This is a convex function, no doubt, because the Hessian is 2 times the identity matrix and therefore positive definite, and hence H is strictly convex. But here we note that if I take this set x1 x2 such that H x1 x2 is equal to 0, this set is not convex. Fine. If it is a non-convex set, then obviously the set of all points, those are satisfying all this. That means the feasible set of the problem is not necessarily convex if Hj is convex. But you want your this f to be convex, because otherwise this problem is not a convex optimization problem, because in a convex optimization problem your objective function must be convex, constraint set must be also convex. But if you just take Hj is convex, then your constraint set capital F is not convex. So what you do here is you take this Aj as affine constraints. That means Aj is a vector, n-dimensional vector, Aj transpose x plus Bj equal to 0. And as you all know, this set of all x's such that Aj transpose x plus Bj equals to 0, it is just a flat region. It is just a hyperplane, right? And a hyperplane is a convex set. So if you now define f capital F, which is set of all x's, set of all points x such that gix less than equals to 0, and your Aj's are Aj transpose X plus Bj, then in this case, this is a convex optimization problem. So I now consider here the first order sufficient optimality condition. It loosely says the following, that KKT point plus convexity of the problem implies optimality. Let me be neat. It says that consider the problem, a constraint problem P, where F and Gi for I equal to 1 to m are convex over the non-empty open convex set capital X subset of Rn, and you take Hj's are given by Aj transpose X. Here Aj is a vector and Bj is a scalar. Then if you suppose that x0 is a KKT point, then, and this x0 is belonging to your visible set, then x0 is a minimum, indeed global, is global minimum point of the considered problem. Okay, now let us try to prove it. The proof goes in the following manner, that what we have to prove, that you take any point x in the feasible region and you have to prove that if x minus fx naught is greater than equals to 0. This will prove that your point x naught is not only local but also global optimum. Fine. Now as the objective function f is convex, therefore this is greater than equals to the first order characterization of convexity, x naught transpose x minus x naught. But as the point x naught is a KKT point, there exists lambda i's all greater than equals to 0, or rather let me take lambda I bar and mu j bar belonging to real number set, such that you have these two conditions, that f x naught plus summation over lambda I bar grad gi x naught for all I equals to 1 to m plus summation j equals to 1 to L mu j bar grad hj naught is equal to null vector. Together with this stationarity, you also have lambda I into gi x naught is equal to 0 for all I. Fine. And here let us plug now this grad f value. Grad f x naught is negative of summation for all over I equals to 1 to m lambda I grad gi x naught lambda I bar j equals to 1 to L mu j bar grad hj x naught transpose x minus x naught. Fine. Fx minus fx naught is greater than equals to, we know that it is your I equals to 1 to m lambda I times you have grad gi x bar transpose x minus x naught. Okay, and you have minus summation j equals to 1 to L mu j bar grad of h j x naught transpose x minus grad of h j x naught transpose x naught. Fine. Now this is equal to, we note that as the function gi are also convex, what you have is gi x naught minus, sorry, gi x minus, okay, let me take here, this plus gi x is evidently greater than equals to grad gi x naught transpose x minus x naught, right? Because gi's are all convex, and this is for every I. So if I restrict even for all I belonging to the active index, then also it is okay. And also what you have, lambda i's for which i's are not in ax naught, those are equal to 0, and therefore it is nothing wrong if I just consider here, to remove this I equal to 1 to m, I just consider here I belonging to ax naught. Fine. And therefore here we know that, and if I take now here negative on both the sides, this inequality will get reversed, and accordingly you will have here negative of I belonging to ax naught lambda I bar into gi x naught minus gi of x. Fine. And you have minus j equals to 1 to L mu j bar. What is gradient of hj? You will find that it is aj transpose, and therefore you will have aj transpose x minus aj transpose x. Now here you note that gi x naught, this quantity, as I belonging to ax naught, so this quantity is equal to 0. So what you are leaving here, that lambda I, which is a greater than equals to 0 quantity, and here gix, as x is a feasible point, so gix is less than equals to 0, and therefore negative of gix is greater than equals to 0. And here aj transpose x, as x is a feasible point, you have assumed x is belonging to capital F, and therefore this is equal to your bj. Similarly, as x naught is also a feasible point, this is also equals to bj. So the second term gets entirely vanished, and the first term gives us a greater than equals to 0 quantity. Fine. And therefore this implies x naught is a global minimizer. Fine. Now here let me conclude the class. Before concluding the class, let me mention you a point which is a common source of error. What do we usually think? Usually convex optimization problems are very well behaved, in the sense that any stationary point is an optimum point, any local optimum point is a global optimum point. However, you sometimes, usually I have seen from the students, that they usually think that any optimum point of a convex optimization problem is a KKT point, but this is not necessarily true. That an optimum point or a minimizer of a convex optimization problem may not be a KKT point. For example, take the following problem, that it is minimization of the function x1. It is a two variable problem. The objective function is x1, subject to x1 minus 1 square plus x2 minus 1 square is less than equals to 1, and x1 minus 1 square plus x2 plus 1 square is less than equals to 1. Now for this problem, if I just quickly draw out the feasible region, we will find the following. And this is a convex optimization problem because here the inequalities are given by convex functions. Objective function is also a convex function, and therefore it is a convex optimization problem. There is no doubt. Now, what is the feasible region here? Here, the first inequality is saying the inside region of the circle centering at 1, 1 and radius 1. So, this is the first circle inside of this circle, and the below inequality says that it is the following circle having center at 1 minus 1. Fine. And therefore, what is the feasible point? It has only one feasible point. It is 1 0 is the only feasible point, and therefore optimizer of the problem. However, at the point 1 0, can you check that this point is not a KKT point? I am giving a home task. Check that 1 0 is not a KKT point of the problem. And therefore, although it is a convex optimization problem, but the optimum point 1 0 is not a KKT point. Why it is not happening? This is due to the fact that the condition that you require in the necessary optimality condition, the constrained qualification, that here the statement of the theorem, this is very crucial. And you check that this condition is not satisfied by the convex optimization problem that I have written, and therefore the point 1 0 is not a KKT point, although it is an optimum point. But as the constraint qualification is not satisfied, therefore the point x0 is not a KKT point. Now with this, let me end up the class here, and I extend my heartfelt thanks for all of your kind presence. Thank you all.